Right, welcome to the VLSI design course. In this lecture, we are going to study some basics about CMOS, that is complementary metal oxide semiconductor. We know that it is complementary, and we know what is MOS. MOS is metal oxide semiconductor. We already know that MOS are of two types. They are pMOS and nMOS. pMOS is transistor that we have studied in our earlier course, the ECD, electronic circuit circuits and devices course, where we have a pMOS like this. We have an n-type substrate and drain and source of type P plus, and then a silicon dioxide layer, and then we have this gate. Right, so this is drain, this is source, and this is gate, which is also called pulley in modern VLSI design. Right, and for an nMOS we have a structure like this, that we have P substrate and we have N plus a silicon dioxide layer and a gate which we call as pulley. So these two transistors are MOS, metal oxide semiconductor. Why are they called metal oxide semiconductor? Because this gate is conventionally made up of a metal. This silicon dioxide, we write only oxide for the silicon dioxide, and this is the semiconductor layer. So that is why we call these transistors the MOS transistors, and there are two types, pMOS and nMOS. And this is what we studied in one of our earlier courses, ECD, electronics, EDC, in fact, electronic devices and circuits course. Right. So today we are going to form some to define a logic family that is based on MOS, and that we call CMOS, complementary metal oxide semiconductor. Why complementary? Because we have equal number of pMOS and nMOS transistors to implement any given Boolean expression using CMOS. That is why we call it complementary. Why complementary? Because pMOS and nMOS are complement of each other. Therefore, we call it complementary MOS. So we have this complementary MOS arrangement to implement any given Boolean expression. So this is a general structure of a CMOS which we can use to implement any given Boolean expression. So this pMOS nMOS array, this pMOS array is connected like we have all the source terminals on top, drains on the left, gates on the left, and drain to the bottom. And all nMOS are connected like they have drain terminals on the top, gate on the left, and source is in the bottom. And the source of certain transistors will be connected to ground. Right. So to make things simple, let's start with the simplest possible circuit, CMOS NOT, where we have this one MP and one MN. MP is a pMOS transistor. We use the word MP, M sub P, the letter M sub P for a pMOS transistor, and we use MN for an nMOS transistor. Right. So a pMOS can be implemented, a CMOS NOT can be implemented with the help of one pMOS and one nMOS, connected in such a way that the source terminal is connected to VDD. The source terminal is connected to VDD. The gate is connected here. The drain is here. And for this nMOS transistor, we have drain connected here, gate here, and source is connected to ground. Right. And we know that that we studied in EDC, that for example for this nMOS transistor we apply a positive voltage to this gate terminal and we apply a voltage difference between drain and source VDS, this voltage difference to drain and source terminals. But since we have one forward biased and one reverse biased terminal, this is forward biased, this is reverse biased terminal, there can be, although there are minority carriers electrons in this P substrate, but they are not enough in this channel to set up a current flow. For that we apply a positive voltage here, and these minority carriers electrons, they are attracted into the channel, and as we increase the magnitude of this voltage, the number of electrons that gather in this channel, their number increases, and once they are sufficient in number to set up a current flow between drain and source, we call that gate voltage, gate to source voltage as VT, and the threshold voltage. So this is the threshold voltage VTN. This is the minimum voltage between gate and source of an nMOS transistor that sets up a current flow between drain and source. Similarly, for this pMOS transistor, we apply a negative voltage here, and minority carrier holes, they are in this n-type substrate, but or in n-well, we'll study n-well later in our later lectures, right? So in this n-type material we have holes, but they are not gathered, they are scattered actually, they are not gathered in this channel. So as we apply a negative voltage, they are attracted, and once they are sufficient number here and they are sufficient enough to set up a current flow between drain and source, we call that voltage as VSGP. So this is threshold voltage. We have one threshold voltage VTN for nMOS and another threshold voltage VTP, that is for the pMOS transistor. So turning it on, turning an nMOS on requires VGS between gate and source of this nMOS transistor to be greater than or equal to VTN, and turning a pMOS on requires this voltage VSG to be greater than a certain threshold VTP, and VTN and VTP, they both are around 0.7 to 1.2. So it's always mentioned. So their values range from 0.7 to 1.2. Right. So let's discuss the operation. Let's discuss the operation of the CMOS NOT, and let's verify whether this given circuit is actually a NOT. How would you do that? Right. So let's see what you are going to apply on the input of this, and let's see what's the status of MP, what's the status of MN, and what is your output. So let's fill this table, and of course this table must have only two entries. When we have 0 volt applied, when we have VDD, the max possible voltage applied. 0 volts corresponds to logic 0, VDD corresponds to logic 1. So if we apply 0 volts here, let's check what is VGS. VGSN would be, this is equivalent to having a voltmeter between this gate and the source terminal. So let's see what the voltage is. This is ground is already at 0 volts, so 0 minus 0, this is 0 volts. So since this is less than VTN, so this means MN is off. Let's check what is VSG. VSG, let's put a voltmeter here to make things simple. Let's put a voltmeter here and check what this voltmeter reads. VSG, so VDD minus 0 is VDD, so this is VDD, and of course VDD is much larger than VTP, turning MP on. This MP is, if this MP is on, this VDD is available at the output, and the output is VDD. VDD means logic 1. So we have logic 1. We have logic 1 available at the output. We have applied 0 volts to the input. We have obtained VDD at the output, logic 1 at the output. The input is logic 0, the output is logic 1. So it meets first condition of, it has fulfilled first condition of being a NOT. Right. Let's apply VDD at the input now. VDD. If this is VDD at the input, V in is, if it is VDD, let's put a voltmeter here and check what is VSGP. So VSGP is, right, VSGP is VDD minus VDD. So VDD minus VDD, it's a 0 volt. 0 volts means MP is off. And what is VGSN? Put the same voltmeter, or if you have another voltmeter, you can put it here and check. VGS, we get to source, VDD minus, this is 0 volts. So VDD minus 0 is VDD, and VDD of course is greater than VDN, and this MN now turns on. So if you apply VDD as the input, this MP is off, MN is on, providing this 0 at the output, or in other words, the output voltage here is discharged through this path, and we get finally 0 volts at the output. Right, so this is how it works, and we have actually established, that this given circuit implemented with one pMOS and one nMOS, and fulfilling these general requirements of a CMOS structure, basic structure, it actually fulfills the requirement of being a NOT, because it has fulfilled, fulfilled the requirement of the truth table. In fact, it's a truth table of truth table. So we have verified the truth table of a NOT using this circuit. So leaving this circuit as a CMOS NOT. Right, that's all for this small lecture. And in the next lecture, we will study about the voltage transfer characteristics that we will study about voltage transfer characteristics that we obtain by performing DC analysis of this CMOS NOT. So voltage transfer characteristics VTC of a CMOS NOT. In the next lecture, we will study VTC of a CMOS NOT. Thank you.